My name is Agnes Janke. I'm the Product Marketing Manager at X-FAB responsible for silicon carbide and gallium nitride. Today I would like to give you a short glimpse about the processing of silicon carbide in the CMOS foundry. X-FAB Texas is a pioneer in silicon carbide technology. The site is since 2099 part of the X-FAB group and is currently running CMOS and silicon carbide on 6-inch wafers. Our silicon carbide engagement began in 2013 with 2 initial customers and then quickly expanding with the membership of the Power America program. It was soon clear that a mere conversion of tools would not be sufficient, so we have quite a long history of adding new dedicated silicon carbide equipment to the fab, most of them 8-inch capable. Today, X-FAB is worldwide the largest silicon carbide pure-play foundry. We are ramping our silicon carbide volumes constantly and expanding the silicon carbide manufacturing capacity. Today, we have several customers running in mass production and even more in development for silicon carbide world-class diodes, JFETs and MOSFETs. Silicon carbide and silicon processes share many common tool sets for manufacturing. But there is also a lot of silicon carbide specific processing steps and tools necessary to manufacture both in parallel. In the past, we added capabilities for silicon carbide epitaxy in-house, added several high temperature implants and annealing tools, both very critical process steps for the silicon carbide MOSFET. We offer thick metal deposition with a polyimide cap, backside ohmic metal and wafer thinning down to 110 micrometer. Let me tell you a little bit about the challenges of processing silicon carbide. You might think that the processing of SiC wafers is as easy as silicon wafers, but quite the opposite is true. X-FAB's engineers faced some major challenges before we have been able to process silicon carbide wafers on a similar yield like silicon wafers. So first of all, silicon carbide is transparent and quite brittle. So there have been made many adjustments to the equipment to be able to handle, mark and measure silicon carbide wafers. The second challenge is the wafer geometry. Silicon carbide wafers have a huge bow and roughness compared to silicon wafers, but are only half as thick. So imagine you try to place a bowl on a flat tray and do some lithography with the same focus depths over the whole wafer. You will fail. And we have the thermally induced bow. Once you heat up the thin silicon carbide wafer, they double bow like a potato chip. Our engineers did a remarkable job at those tools. They managed to get the yields on those tools way below 1%. The equipment manufacturers supply the same tools with their best-in-class process with around 25% yield loss. The third challenge lies in the physical difference between the silicon carbide and silicon lattice. In silicon, you implant the dopant on the surface, and through diffusion, the doping layer is created. This will not work for silicon carbide. Here, practically no diffusion takes place. The dopants stay where they have been implanted. The only way to achieve selective doping is to use multiple implant steps to create a box profile, which creates a low throughput through the implanters. That's why the implant schedule is so crucial for the device characteristics. You basically need to shoot the atoms with the right angle, energy, dose and temperature into the place where they need to be. So here lies a lot of knowledge, as you can imagine. With the implant at such aggressive conditions, you are basically creating a moon surface on the wafer. Post-implantation annealing is required for lattice recovery and electrical activation. A carbon cap is used to avoid surface roughening. Without the carbon cap, the silicon atoms will preferably leave the silicon carbide surface. As you know, we are talking about power devices, and this means a high current density that require very thick metals at the surface. On the other hand, devices in the 600 volt up to 1700 volt need the wafer to be thin. The thinner, the better for the RDS(on). So the stress handling of the silicon carbide wafers becomes a huge issue. And last but not least, there are the challenges in the device design. There is simply no perfect design, but just carefully balanced trade-offs between, for example, the blocking voltage and the RDS(on). So to summarize it, to process silicon carbide wafers in a silicon foundry is quite a challenge. Let me explain you some insights about the foundry business model. In the traditional foundry model, the foundry experts develop technologies that customers can use to manufacture their own integrated circuits. This is the so-called open foundry platform technologies, broadly used for CMOS or BCD on SOI technologies, also at X-FAB. The customer gets a comprehensive set of tools like a PDK, the process design kit, which contains typically a primitive device cell library with P cells and IP blocks, simulation models, and design rules, among others. The device design lies in the responsibility of the customer. A different approach is used when other players, so-called fab-lite partners like IDMs or even other foundries, want to outsource their technology into a foundry. Then that needs to be copied exactly. Both approaches do not work for wide bandgap technologies. First of all, silicon carbide or gallium nitride chips usually contain a single discrete device, like a MOSFET or a diode. This means that the foundry cannot provide already a parameterized cell for the transistor. This would leave no room for competition between its customers. All devices would have similar characteristics. But indeed, there are a lot of potential ways to optimize also a large single transistor. Characteristics like cell size, RDS(on), or breakdown voltage need to be balanced and optimized for the application. There is simply no one-design-fits-it-all solution. That's why for the manufacturing of silicon carbide or gallium nitride devices, the customer needs to have a much deeper understanding, not only of the device design itself, but also of the process steps that will determine the parameters of the device. This is where X-FAB's unique approach comes into place. X-FAB developed a comprehensive set of unit processes that can be used modularly to develop a power device. This way, customers can balance the device characteristics to their target and be competitive in the market. The process integration is supported by a PDK Lite, a similar set of files like in the open platform technologies, but without characterized P cells. Our organization will support the customers in the implementation, giving them a head start for a fast time to market. So how does this look like in reality? Well, to be honest, we end up with a bunch of different processes, usually even several different flows per customer. Those processes might not even differ much in their outcome, but each needs to be handled separately. And this is where X-FAB came up with a specific approach. 2 years ago, I was here at Bode's conference and presenting our standard process block approach. This meant that for each of those little sub-processes, X-FAB developed a set of recipes with the best practice approach to run this process at our line. But this still meant having to handle a huge number of technologies, which is limited by our resources. So we went one step further and developed a more narrowed and streamlined technology that we call X-Blocks. So what is X-Blocks? Well, basically it's a new business process that enables customers to create their own specific MOSFET technology. It is still based on our standard process block approach, but with a limited number of module offerings. This means, for example, that instead of offering a solution for every nanometer of variation in gate oxide thickness, the customer can choose between 3 options: 35, 40 or 50 nanometer. That's it. Those qualified process modules are optimized for tool utilization, yield, and common use. Additionally, we streamlined the overall business process. Automated process questionnaire and access to the X-FAB hotline will enable faster onboarding. A robust set of design rules is implemented into various EDA design software, basically a PDK without the P cells. Control plans, MES setup, FMEAs, testing, all service processes have been simplified to allow a faster move into production. Will the X-Blocks program replace the customer-specific developments? No, we will still support customers with their specific demand for highly optimized silicon carbide devices. Here, customers will have a dedicated process development engineer supporting them and full flexibility for the process modules. But we are inviting customers to check if the X-Blocks program might not be sufficient for them, as it gives them a head start in time, faster onboarding, faster cycle time, and shortened development cycles. And this is a big advantage. Customers can move faster to process freeze and risk production and bring their products faster to the market, around 9 months earlier compared to a customer-specific development. Our X-Blocks program will be expanded steadily. We will develop further process modules and will have also included a silicon carbide diode in the future. Generation 2 of the X blocks will enable reduced feature sizes for even smaller planar MOSFET devices. And with the X blocks Plus extension, we will give our customers the opportunity to develop one additional customized process module to diversify their product even more from the competition. So where are we heading? X-FAB's foundry offering for silicon carbide devices is well received in the market. We are currently serving a majority of the fabless silicon carbide players and will maintain that share in the future. Silicon carbide is growing at a very high growth rate in the market, and we are heavily investing into expanding our silicon carbide capacity as well as the technology offering. We will further improve our planar technology offering, but we will also add trench capabilities for our customers. With that, I'm coming to the end of my presentation. Thank you very much for your attention. If you have any further questions, feel free to contact me.